ring has only one law of composition. It only has addition. It doesn't have multiplication. Anyway, so shall we start today's lecture then?
Yes, sir. Yes, sir.
Okay, so I'll start this presentation. Can you see my slide now?
No, sir. Yes. Yes, sir. Yes, sir.
And if do you continue to see it? Everything is visible?
Yes, sir. Everything is fine.
Yes, sir.
Okay, so let's start. You see, there's this notion of exact sequences. Or before I talk about exact sequences, let me recall what we did last time. Essentially, we gave a lot of definitions last time. What are modules? What are linear combinations? What are submodules? What are quotient modules? That's about it. Now, you see, you need to develop this terminology in order to come to interesting results. You need to have the words. So that's what we had introduced. Here is another piece of terminology called exact sequences. So if you have an A linear map U from an A module E to an A module F, then there are two submodules associated with U. There is the kernel of U, which is submodule of E, and it's a set of all x in E such that U of x is 0. Then there is the image of U, which is a submodule of F, and it consists of all y in F, which are of the form U of x for some x in E. Okay, so that's a very simple concept. It makes sense for homomorphisms of groups as well. And it's easy to check that this kernel of U and image of U are submodules of E and F, respectively. There's also this thing called the co-kernel of U, which is F This is the same as the co-kernel of U being 0. Okay, so these are then we say that this sequence E to F to V to G, given by the linear maps U and V, is exact. So to say that the sequence 0 to E to F is exact is the same as saying that this map U is injective. Similarly, to say that the map in the sequence F to G to 0 is exact is the same as saying that V is surjective. Okay, so we need to have many different ways of saying the same thing. That makes the language more supple. So, for example, if I have a submodule E prime of an A module E, then I can write down this sequence: E prime going to E modulo E prime. Right? When you take the quotient, there is always a map from the module to the quotient, the projection map. And this sequence is exact, more or less by definition, because E prime to E is injective, it's a submodule, and E to E modulo E prime is surjective, because that's a quotient of E. So whenever you have a submodule, you have this exact sequence, and such an exact sequence is called a short exact sequence. A short exact sequence is one in which you have three terms, and you have zeros at both the ends. Similarly, if you have an arbitrary A-linear map U from E to F, then you can write down this sequence, which is kernel of U goes to E. The kernel of U is a submodule of E, of course. Then you have the linear mapping U from E to F. From F, you have a map to the co-kernel of U, and that's surjective. So this sequence is also exact. This is a 4-term sequence. Short exact sequences are 3-term exact sequences. Okay. So we come to a very important that you have to have a family of A modules. For a family, you have to have an indexing set. So I is the indexing set here. And for every iota in I, you have an A module E iota. Then these modules are, after all, sets as well. You can take the product of all these sets. You first have to make it into a group. Pi kappa from E to E kappa, all these maps become A-linear. Okay? So this construction of the product has what is called a universal property. And what is this universal property in this case? It says that if you have some module, A module F, and maps pk from F to P kappa, from F to E kappa, these are A-linear maps. Then, so I've drawn this red diagram here. You have the product. So this is for just two modules. I can't do it when the set I, the indexing set I, has arbitrary many elements. Let's do the simple case when it has just two elements. So this is E is equal to E1 cross E2. Is the product of E1 and E2. Here it is, the product. If I have some other module F and maps from F to E1 and from F to E2, then there's a unique map, A-linear map from F to this product, such that this map is this composite and this map is this composite. So there's a unique map. The dotted arrow is the one whose existence is being asserted, which makes these two triangles commute. Okay, so this is the analog of the product set in the category of sets. You have the product group in the category of groups. Similarly, in the category of modules, you have the product module of any family of modules. Okay, so it's defined as a submodule of the direct product. So if you have a family of A modules E iota, you first get all those families of elements X iota, such that X iota is 0 for almost all iota. What does almost all mean? It means X iota is actually 0 for every iota, but they are so this from each E kappa into E. It sends an element X kappa of E kappa to this family Y iota, iota in I, where this Y iota is equal to X kappa if this iota is equal to kappa and it's 0 otherwise. Okay, so this is the standard thing which you do. Now what I've got is, given a family of A modules, I've got their direct sum and a family of maps from each of the modules to the direct sum. And this pair consisting of this module, which is the direct sum, and the maps from each of the modules in the family to the direct sum, this has a certain universal property. Just as for the direct product, you had this universal property. Similarly, for direct sums, you have this universal property in the red diagram here. I've drawn this diagram only for 2 modules. So if I have 2 modules, E1 and E2, the direct sum is written E1 plus E2 in this, and plus with this circle around it. That's a direct sum. It comes with maps from E1 and E2. These are A linear maps. And the universal property is that whenever I'm given some A module M and A linear maps from E1 to M and from E2 to M, there is a unique A linear map from the direct sum to M, which makes these 2 triangles commute. So, it might be interesting for you to think about the notion of direct sum in the category of sets. So suppose I'm given 2 sets. These are not A modules anymore. These are just sets. E1 and E2 are 2 sets. Can I find, so this is an exercise, can I find a set which will be called the direct sum of these 2 sets, and which has the property that whenever I'm given a map from E1 to some other set and from E2 to that set, there is a unique map from the direct sum to this other set, which makes these 2 triangles commute. For the direct product, for the sets, you get the same thing. I mean, it's a direct product of sets. You know that. But maybe you're not familiar with this notion of the direct sum of 2 sets or of a family of sets. But that's also an important notion, and I leave it to you to try to figure out what it should mean, whether any 2 sets have a direct sum. It's not the union, because the union, some of the elements might be in common, whereas so you think about it, how it's different from the union of these 2 sets. Okay. Now, another thing which you can do with a family of modules is, now this is not a family of arbitrary modules. These are all submodules of a given module E. Then you can take their intersection. And it's easy to check that this intersection is again a submodule of E. Okay? So, you see, these are all little checkings which I'm confident you are all able to do. So, one needs to check that, for example, if it's a submodule, 0 has to belong to this intersection. Why does 0 belong to it? Because 0 actually belongs to each of these submodules. So it belongs to the intersection. Given any two elements of the intersection, their sum has to belong to it. Why does it belong to it? Because the sum belongs to each of the submodules m iota, etc. I mean, this kind of verifications are best left to you people. Now, let's look at what is this saying? It says that this sequence is exact. So 0 to the intersection to E to the direct product of this family. What is the family? The E modulo m iota. For every iota in I take the quotient E modulo m iota and I take their product. What is the map from E to this product? Well, there's a map from E to each of the factors. And therefore, you get a map. So X goes to pi iota of X, where pi iota, to the family consisting of pi iota of X, where pi iota of X is the image of X in E modulo m iota. And why is this sequence? So I've explained what the sequence is. Now I'm saying that it's an exact sequence. Why is it exact? The only thing which needs to be checked is that the kernel of this map here is equal to the image of this map. The image of this map, this is the inclusion map, so the image is the intersection of the m iotas. So basically what this is saying is, the exactness of this amounts to saying that the kernel of this map is the intersection of the m iotas. And that is clear because the kernel of pi iota, the map from E to E modulo m iota, the kernel of that map is m iota. And when I take the map into the diagonal map into the product, the kernel is going to be the intersection of all the kernels. And that's what is written. Okay. So let's come to another easy statement. Suppose I have two modules E and F, and I have a linear map U between these two modules, and then I have a subset of the module E. Then I can talk about the submodule generated by this subset. We already talked about it earlier, and earlier we had seen that this submodule is the set of all linear combinations of elements of capital S. I don't remember whether we talked about this being the same as the intersection of all submodules of E containing capital S. But that's another way of looking at the submodule generated by S. It's either the set of linear combinations of all elements of S, or it's a set of it's the intersection of all submodules of E containing S. These two are the same, of course. So the assertion here is that the image of this submodule M generated by this subset S is generated by the image of the set S. So UM is generated by US. This is the assertion. How do you check this? So M, as I recalled, is the set of all linear combinations of elements of S. Now, if I take a linear combination, it's an element like this, with these alpha S are in the ring A, and almost all of them are 0, with finitely many exceptions. Then U of X is going to be this. Why can I write U of X like this? Because U is a linear map, U of this whole sum is the sum of these things, and these alpha S also come out in some sense, right? So you can see that U of X is a linear combination of elements of U of S. Similarly, if I have a linear combination, this is a step which should have been written, it's not here. It says that if I have a linear combination of elements of U of S, then it's the image under U of some linear combination of elements of the set S. Okay, so it's more difficult to say it than to sort of think about it and write out what is involved in convincing yourself that if you take the submodule generated by a subset, its image is generated by the image of the subset. Okay, so we are talking about modules being generated by some subsets, right? So suppose I have a short exact sequence, 0 to E to F to G to 0. That kind of a sequence, exact sequence of modules is called a short exact sequence. Okay? So suppose I have a short exact sequence and I have a subset S of E which generates the module E. And I have a subset T of F. F is here in the middle. I have a subset T of F such the image of T under this map, little g, which is of course a subset of capital G, generates the module capital G. The claim is that in this case, the image of S, F of S, union T will generate the module F. So basically, what is being said is that if I have a set of generators for E and a subset whose image generates G, then their union generates F. This is what is being asserted. Now this needs some proof, and here is the proof. So we are claiming that this set generates F. In other words, we have to show that every element of F is a linear combination of elements of this set. So it's enough to show that every X in this E is incorrect. It should be F. It's enough to show that every X in F is a linear combination of elements of this subset. That's what we have to show. Okay, so let's take this X and let's look at its image in this capital G. Let's look at G of X in capital G. Now, it's given to us that this G of T generates capital G. Therefore, G of X, which is an element of G, will be some linear combination of elements of this G of T. But every element of every linear combination of elements of G of T is the image of a linear combination B of elements of T. So, in other words, G of X is G of B for some B, which is a linear combination of elements of T. How did we get this conclusion? We use the hypothesis that G of T generates capital T. Now we'll use the hypothesis that this S generates E. So let's look at X minus B. X minus B, what is G of X minus B? It's 0 because G of X is equal to G of B and G is linear. So G of X minus B is 0, which means that X minus B is in the kernel of G. But this is an exact sequence. The kernel of G is equal to the image of F. So that's what I've written here. The kernel of G is the image of F. So X minus B is the image of some little a in X minus B is the image of some little a in E. But this F of A is a linear combination of f of s, because A is a linear combination of elements of S. Finally, so this x minus b was equal to f of A, which is the same as saying that x is equal to f of A plus b. This is a linear combination of elements of T, and this is a linear combination of elements of f of S. So x is a linear combination of this union. Okay? I think I've done it in gory detail. Usually one doesn't get down to such fine detail. Many of these things are sort of left for you to verify. In any case, so here is a small corollary of this proposition. It says that whenever I have a short exact sequence E to F to G, and if E and G are finitely generated, what does that mean, finitely generated? It means that there's a finite subset which generates them as modules. There's a finite subset of which every element in the module is a linear combination. So if F and G are both finitely generated, then the middle module F is also finitely generated. Okay, so maybe I'll stop for a few minutes to see if any of you have any questions. You have 2 minutes to, oh, your voice is breaking, no audio.
So there is a huge congestion in the voice.
Oh, goodness.
Sir, I have a query, sir.
Yes.
Is it working with if I'm just dealing with the left or right module alone, all these things would work over there?
That's exactly
rather than on module.
Yes, so you have to be working with either with left modules or with right modules. So module here, I'm assuming that they're all left modules. Yes,
left only.
They all work in
Okay,
this
sir.
generality.
Thank you, sir.
Yeah, so I wish somebody would have should have interrupted me. Can you hear me properly now, or you can't hear me?
Right now it is fine, sir. For me, it is fine, at least.
Okay. Are there any other questions? So I'm really sorry that this audio is not working properly sometimes, but well, I don't really know. Okay. Right. So let's go to the next slide. It talks about the internal sum of submodules. Okay. So what is this internal sum? We have talked about the direct sum of a family of modules. Here we are talking about a somewhat relative notion. Here all the modules happen to be submodules of a given module. So you have a ring A, you have an A module E, and for each iota in I, you have a submodule M iota. So of course you can talk about their direct sum, which we had done earlier. For talking about these direct sums, the modules don't need to be submodules of a given module. But when they are submodules of a given module, what you have is a map, a linear map, from the direct sum to the ambient module. The ambient module is the one of which all these M iotas are submodules. And what is that map that I'm talking about? It sends a family, X iota, to the sum of all these X iota. Why can I take the sum of possibly infinitely many X iota? Because almost all these X iota are actually zero. Only finitely many are different from zero. Okay, so let me repeat. When I have a family of submodules of a given module, I have a linear map from the direct sum of that family to the ambient module, given by this. This is an A-linear map, so it has an image. The image of F is called the internal sum of these submodules, and it's denoted by this sigma, not by this plus thing, which is reserved for direct sums. This is just an ordinary internal sum. Okay? So that's the definition. It's the image of this map F. You can check that it's also the submodule of E generated by the union of these M iotas. You see, the intersection of two submodules is again a submodule, but the union need not be a submodule. You can already see it for R2, for example. If you're familiar with R2, then you have the x-axis and the y-axis. They are both subspaces, but their union is not a subspace. Okay? And but it's a subset and it generates a submodule. So that submodule happens to be equal to the internal sum of these modules. Another description of this sum is that it's a set of all finite sums x iota, where x iota is from M iota. Again, I can take these directs. Again, I can take the direct, it's not a direct sum. It can take the sum of these x iota because almost all of them are 0. So here is what happens when you have just two modules, M and N, submodules of some module E, and if I denote by I and J the inclusion of M and N into E, then I have a mapping M plus from M direct sum N to E, and that mapping is going to be called I plus J because it takes X, Y. Elements of this are pairs X, Y, where X is from M and Y is from N. It takes this pair X, Y to I of X plus J of Y. I can take this sum in the module E. And the image of I plus J, this map I plus J, is precisely the submodule M plus N. So as I said, when you have two submodules M and N of the same module E, you can take their direct sum or you can take their simple sum inside the module E. How are these two related? Is there some sort of relation between them? We already know one relation that, M plus N is a quotient of M direct sum N. That's how it was defined here. Now it's the image of this map F which sends the direct sum into E. Anyway, so here is this little red square which sort of summarizes what modules I'm dealing with and what are the... So these are all submodules of M plus N, and these are all inclusions. M going to M plus N, it's a submodule of M plus N. So is N, and the inclusion is called J. And M intersection N is a submodule of M as well as of N. Okay? So here is a map delta from M intersection N to M direct sum N. So this intersection is a submodule of M as well as of N. So if I take an element X, I can send it to the pair X, X. This is sometimes called the diagonal map. It's when you have the plane R2, the line XX defined by Y equal to X, that line is sometimes called the diagonal or the principal diagonal, right? So I have this delta which takes x to x comma x, and I have this map I minus j from m direct sum n to m plus n, and it takes a pair x comma y to I of x minus j of y. I of x and j of y are both elements of m plus n. This is an element of m and this is an element of n, but they are both elements of E where I can take their difference. So the claim is that this exact sequence 0 to m intersection n to m plus n to m plus m direct sum m, m direct sum n to m plus n to 0. This short exact sequence is what is being asserted, that the sequence is exact, right? So what do we need to prove in order to show that this sequence is exact? There are 3 or 4 things. The first one is that delta is injective. Now, delta is injective is absolutely obvious because it takes x to x comma x. Okay? So, the kernel of this map is 0. The only one which goes to 0 here is 0, right? So it's injective, that's clear. Now, the second thing to check is that I minus j is surjective. This map I minus j from here to here is surjective. Well, it's going to be surjective if its image contains m as well as n, because m plus n is the smallest submodule of E containing m as well as n. Okay, so in order to, and the image of I minus j is also a submodule. So if I can show that m and n are containing this image, I will have proved that I minus j is surjective. Okay, so what is I minus j of m direct sum 0? You know, m direct sum 0, think of it as a submodule of m plus n, or rather m direct sum n, submodule of this. So that's taken to m. Similarly, the image by I minus j of the submodule 0 direct sum n, this submodule here, is n. So the image of I minus j contains both m and n, and therefore it contains m plus n. And it's easy to check that it's surjective. I mean, it doesn't contain anything more than m plus n. So I minus j is surjective. And the third thing which we need to check is exactness here, which means that the image of delta is the same as the kernel of I minus j. Now, the image of delta consists of all pairs xy such that y is equal to x. And what does the kernel of I minus j consist of? It consists of all pairs xy such that ix minus jy is equal to 0. Actually, I and j are just inclusions. So that amounts to saying that x minus y is equal to 0. And that amounts to saying that x is equal to y. So that's what I've said here. The image of delta is equal to the kernel of I minus j, because each of these submodules consists precisely of those pairs yz in m direct sum n, such that y is equal to z. Okay? So here is another exact sequence in red, okay, which follows from the exactness of this sequence here in blue. The sequence in red, how is it different from the one in blue? This is the one in blue, and this is the one in red. Here I had I minus j, whereas in red I have I plus j. And here I had delta, whereas in red, I have delta prime. And delta prime is the map which takes x to x comma minus x. So it's not the diagonal, it is sort of the anti-diagonal. Okay? So instead of x going to x comma x, I have x going to x comma minus x. I'm claiming that this sequence is also exact. And how do I prove it? Well, one way of doing it is to repeat this argument for this new sequence. You can repeat the same thing and you'll get a new proof. You will get a proof of the exactness of this sequence. Another way is to use this and to derive the exactness of the red sequence from the exactness of the blue sequence. And how do I do it? By comparing these two sequences. So these two sequences, if I want to compare them, I see that the first terms, M intersection N, M intersection N, they are really the same. I have the identity map, which is equality in some sense, right? Similarly, M plus N and M plus N have the identity map. In the middle, from M direct sum N to M direct sum N, I have this map which takes y comma z to y comma minus z. Okay, that's certainly an isomorphism. Because for any group, commutative group, or any module, the map sending x to minus x is always an isomorphism. So now I have these three vertical arrows, all of which are isomorphisms, and these two squares which I get, they commute. They commute almost by the definition of delta prime and this vertical arrow. Similarly, the definition, here it was I plus j, but here it is I minus j. And it commutes because this will send yz to y minus z, etc. So, because I have these three vertical isomorphisms and the diagram and the two squares commute, I can deduce the exactness of the red sequence from the exactness of the blue sequence. Okay? Okay. So similarly, here I had compared M direct sum N with M plus N. Similarly, I can compare the quotient M modulo M plus N, right, with M modulo M, E modulo M, direct sum E modulo N. So the situation is the following. I have an A module E and two submodules M and N. So as before, I have this diagram. I have M intersection N, which is contained in M, which is contained in M plus N. And similarly, M intersection N is contained in N and in M plus N. So this diagram, this square here, gives rise to this red square. So these are all submodules of E. So I can take E modulo M intersection N. And I can take E modulo M. And there's a natural map from E modulo M intersection N to E modulo M, because this M intersection N is a submodule of N. So, for example, if you have a commutative group and a subgroup of the subgroup, when you go modulo the smaller group, you have a map to the quotient modulo the bigger subgroup. So that is what is happening here. Similarly, this is what is happening here. So the vertical arrows and the horizontal arrows are both kind of arrows come from the fact that I have this diagram of submodules of E. And these arrows have been called R, S, P, and Q. So from this, I get a sequence E modulo M intersection N going to E modulo M, direct sum E modulo N. In this map, I'm calling it delta. It takes X to Rx, comma Sx. R is this map, S is this map. Similarly, I have a map. When I say map, these are all A linear maps. I have an A linear map from E modulo M, direct sum E modulo N, to E modulo M plus N. It takes a pair Y comma Z to P of Y, because Y is an element of E modulo M, minus Q of Z, because Z is an element of E modulo N, and Q of Z makes sense. P of Y and Q of Z are both elements of the same module, so I can take their difference. And as before, what is being asserted is that this sequence is exact. Okay? So what do I need to check for exactness? I need to check that delta is injective, that P minus Q is surjective, that the image of delta is equal to the kernel of P minus Q. That's what it means for this sequence to be exact. These four things, three things: injectivity of delta, surjectivity of P minus Q, and the equality of the image of delta with the kernel of P minus Q. But that third thing, this last thing, is actually a combination of two things. And the two things are that the image of delta is contained in the kernel of P minus Q, and that the kernel of P minus Q is contained in the image of delta. So we will check these four things now. First, P minus Q is surjective. Okay, P minus Q is surjective because let's, for example, so this is where P minus Q is. Let's look at just this submodule E modulo M of this direct sum. What is its image? Its image is the whole thing. It's the map P restricted to E modulo M. What I have is the map P, this vertical map here. And that is, of course, surjective because it's a quotient of E modulo M by, by what? So I have E modulo M, and then inside this, I have a submodule, which is M modulo M plus N. M, or rather the other way around. So yeah, the other way around, it's M plus N modulo M, that's a submodule here. When I take E modulo M plus N modulo N, I get this quotient here. And therefore, this is a quotient map, and therefore it is surjective. Okay. Similarly, this map delta, why is it injective? Because, excuse me. So, suppose I take something in the kernel of delta, that's going to be an element X in E modulo M intersection N, such that R of X is 0 and S of X is 0. Now, if I take any representative X tilde of X in E, a representative means an element X tilde whose image modulo M intersection N is X. So, the fact that R of X is 0 implies that X tilde is an M. Because the kernel of this map R is precisely elements of M, is precisely M modulo M intersection N to be exact. Anyway, so this, if I take the image in X E, then this X tilde will be in M. Similarly, S of X is 0 implies that X tilde is in N. So if both of them are 0, it means that X tilde is in the intersection. But the intersection, if X tilde is the intersection, then its image X in E modulo M intersection N has to be 0. So that's how I conclude that this map delta is injective. Okay, I take any x which goes to 0 under delta, and I conclude that x is 0. Okay, so now it remains to show that the image of delta is contained in the kernel of P minus Q, and that the kernel of P minus Q is contained in the image of delta. So let's do this one first. This one is very easy. So to show this inclusion, I have to show that when I take P minus Q of something which is in the image of delta, I get 0. And here's what it is. P minus Q of R of x, comma, S of x is P of the first thing minus Q of the second thing, right? P of R of x minus Q of S of x. But look at this commutative square. P followed by, or rather R followed by P is the same as Q, is the same as S followed by Q. P composed with R is the same as Q composed with S. And therefore, this difference is 0. And therefore, I get this inclusion. Let's prove the inclusion in the other sense. And this is slightly tricky. This is the only place where you might have to use a little bit of cleverness. Very little, but some bit. Okay, so let's go through this. I've redrawn the square, the red square over here, R, S, P, Q, etc. And I have to show that the kernel of P minus Q is contained in the image of delta. Okay. So let's take some yz in the kernel of P minus Q. Y, comma, z. So y is in E modulo M and z is in E modulo N. And it's in the kernel of P minus Q means that P of y is equal to Q of z. That's the definition of the kernel. P minus Q takes y comma z to 0, but it takes y comma z to P of y minus Q of z. If P of y minus Q of z is 0, means that P of y is equal to Q of z. Okay. So these two elements y and z, let's take lifts y tilde and z tilde of these two elements in E. What does a lift mean? It means an element of E which, when I go modulo M or N, as the case may be, I get back y or z. Y tilde, the image of y tilde in E modulo M is y, and the image of z tilde in E modulo N is z. Okay, so this y tilde minus z tilde. If I look at this element and I look at its image in E modulo M plus N, it's going to be P of y minus Q of z, which is 0. So this element y tilde minus z tilde is in M plus N. Okay? So that doesn't mean that y tilde is in M and z tilde is in N. Not at all, right? But what it means is that I can find an element A in M and an element B in N such that y tilde minus z tilde can be written as A minus B. So it's equal to A minus B for some A in M and B in N. Now let's look at this element x tilde, which is y tilde minus A, and it's also equal to z tilde minus B, right? Y tilde minus A is equal to z tilde minus B. Let's call it x tilde. The common value of these two things is x tilde. And let's look at R of x tilde. What is R of x tilde? Because x tilde is equal to y tilde minus A, it's the same as R of y tilde minus A. But A is in M, yeah. See, A is in M. So R of y tilde minus A is the same as R of y tilde. But that's equal to y. This is how y tilde was defined. Similarly, when I take S of x tilde, instead of taking S of but x tilde is also equal to z tilde minus b. So s of x tilde is the same as s of z tilde minus b, but b is in n. This should not be m here. It should be n, b is in n. And therefore, this is just equal to s of z tilde. But that, by definition, is equal to z. So now if I put x equal to the image of x tilde in E modulo n, E modulo m intersection n, then I see that delta of x is equal to yz. So what does that achieve? It achieves the proof that the kernel of p minus q, we had started with an element yz, which is in the kernel of p minus q, and we have written it as the image of some x, the image under delta of some x. So we have shown that this kernel is contained in this image. And with this, we have completed the proof that this short sequence is exact. Okay? So let me just summarize the last part of the proof, which is the only tricky part. The rest of it is straightforward. So what is the tricky part? I had an element y and z. That's the first stage. I had two elements y in E modulo m and z in E modulo n, which went to the same element in E modulo m plus n. P of y was equal to q of z. That was the first. That's what I started with. Then I can take the lifts y tilde and z tilde of y and z in E. Okay? This is stage 2. So I have y tilde, z tilde in E. From this y tilde, z tilde, I somehow cooked up an x tilde. This was really the only place where we used the fact, somewhat cleverly, that this difference is in m plus n, so it can be written as a minus b for some a in m and b in n. And x tilde was then defined as y tilde minus a, which is equal to z tilde minus b. Okay, so, and this x tilde was the third stage. Now, it was easy to see that this x tilde goes to something of which the r is y and the s is z. R of x is y and s of x is z. And that completes the proof that the kernel of p minus q is equal to the image of delta. And that this sequence is exact. Okay, so I'll maybe stop for another 2 minutes to see if there are some questions. Are there any questions? Hello? Yes? Hello, is everybody there? Anyway, so I have maybe just a few more slides. So, okay. So here is a notion which is slightly different from the internal sum of some modules. This means, so I have an A module E and some family of submodules m iota. I can take their direct sum as before. And as I said, I have a linear map from this direct sum to E, which takes the family x iota to the sum of these x iota. Now we will say that E is the direct sum of this family if this S iota is an isomorphism. Okay? So if I had just two modules, Right here, it's right here. So m plus n is a direct sum of m and n if and only if m intersection n is 0. That's what we have seen. We have this exact sequence here. Where is it? Yeah, here it is. So m plus n, the direct sum, to m plus n, I have this map. By definition, we will say m plus n is the direct sum of m and n if this I plus j is an isomorphism. And because this sequence is exact, it's going to be an isomorphism if and only if this m intersection n is trivial, is 0. Okay, so that's what happens for two modules. And this is my last proposition for today, of which maybe I'll skip the proof. It's there in the notes, and if somebody is interested, they can write to me. So the proposition states that in general, the following conditions are equivalent. Whenever I have a module E and a family of some modules m iota, I can take the internal sum of this m iota. This is going to be a direct sum of this family in this sense, which are defined here on this slide, is equivalent to the mapping S iota being injective. I mean, that is more or less obvious. I mean, that these two are equivalent, more or less by definition, because this mapping is always surjective, and I want it to be an isomorphism, so it just needs to be injective, right? So 1 and 2 are obviously equivalent. But the third property is slightly less obvious. It says that for every finite subset J of I, the map from the direct sum of m iotas with iota in J to E is injective. Okay? And the last property is that for every kappa in I, the intersection of m kappa and the sum of the remaining m iotas. So here again, there's a typo. This is not m kappa, it should be m iota. The intersection of m kappa and the sum of over iota, different from kappa, of m iota is different from, this intersection is equal to 0. So these four properties are equivalent. First and second are obviously equivalent, and the others, I've checked it here, so you can look at the notes. Since I'm already 6 minutes over time, I'll not go through it. I do one more thing to talk about, but maybe I'll do it next time, right? Here is where the proof of this proposition ends here. And here is an example. So for example, if I have 3 submodules, M, N, and P of the same module E, then when is E the direct sum of these 3 modules, M, N, and P? When is it the direct sum? For 2 N should be trivial, 0, and M plus N should be equal to E. For 3 submodules, the condition is that M intersection N plus P should be 0, P intersection M plus N should also be 0. So I'm slightly over time, so I'll stop here. Are there any questions? Hello?
Any participant have any question?
Yes? Sanjay, any questions?
Actually, I asked other participants, but I think they have no question. So if there is no question, then just let's clap the speaker.
Thank you, sir.
Yes, and for
Thank you, sir.
tomorrow's plan is that there is one tutorial at 3:30 p.m. and after that tutorial we have a third lecture by Professor Dalawat. And in tutorial you can share if you have any doubt and anything in lecture note. Most probably we'll try to figure it out. Okay? So feel free just to ask questions because it is for everyone to interact.
Yes, sir. Thank you, sir.
Okay. Thank you to everyone.
Yeah, we had a problem today. Half the lecture was not audible. So if
Yes,
you
yes.
could send the slides, we have to go through them.
Yes, yes. So just check Google Class folder,
Yeah,
and
yeah,
we
yeah.
are
Yesterday's
uploading
lecture I got.
yes. So most probably after 15 minutes, you will get a lecture 2 and its video also there. Okay?
Thank you very much. Thank you.
And yes, any
Okay.
other question? Yes, sir. Thank you.
Right. Yeah.
Thank you, sir.
Most probably we'll update this upload assignment also. So you can check assignment